In this video, we're going to look at how to solve problems involving linear ladders or linear rods. Particularly, we want to find the coefficient of friction between the ladder and the ground. There are 4 general steps that you need to work through. Step number 1 is that we need to detail a force diagram. Step number 2 is that we need to resolve vertically. Step number 3, we need to resolve horizontally. And step number 4, we need to take moments about the point A. A will be the point where the ladder meets the ground. By moments about A, if the ladder is in equilibrium, in this case it is in limiting equilibrium, that means that the clockwise turning effects, so when the force acts on the ladder, it will be tending to push it in a clockwise direction, must perfectly balance the anti-clockwise turning effects. So when this component of the force touches the ladder, it is tending to move it in the anti-clockwise direction. So the distance between the pivot point A and the contact point of the anti-clockwise turning effect force, that product, X times R1, will perfectly equal to this product, Y times R2. So let's walk through the application of the series of steps. So step 1, we have started it by doing the force diagram. So we know that at point A, there will be a normal contact or a reaction force, and I'm labeling that as RA. We also know that it is resting on rough horizontal ground, so there's going to be friction, and friction will act in the opposite direction to the motion of the ladder, left on its own devices. Additionally, the ladder is leaning against the wall, and the wall is smooth, so there's going to be a reaction here, and we're going to decompose that reaction. So how I've gone to decompose is the following. We know that this is 30 degrees, this is going to be right angle, this is 90 degrees, this is 60 degrees. I'm first decomposing the weight of the load. So we're told that there's a load of mass 3m fixed on the ladder at point C. So that weight will be 3 mg. This angle and this angle will always be the same. And this will be the perpendicular component of weight, perpendicular to the ladder. And this will be the parallel component of weight, parallel to the ladder. And applying SOHCAHTOA, this part would be 3 mg cos 60, this part would be 3 mg sin 60. Similarly, we're told that the ladder is modeled as a uniform rod. What this means is that the weight will be acting down the center of the rod. So the mass of the ladder is m, so the weight will be mg. When we resolve it, we're finding the component of weight that will be perpendicular to the ladder, which will be mg cos 60, because this angle and this angle will always be identical. And then the component of weight that will be parallel to the ladder will be mg sin 60. Here, where we have a reaction of the ladder against the wall, RB, again, we're going to resolve RB, find the component perpendicular to the ladder and parallel to the ladder. Using the geometry of parallel lines, we know that 60 degrees, that these are alternate angles, therefore this is 60, if that is 60. Because this angle is 90 degrees, since this is perpendicular to the ladder, then 60 from 90 leaves us to 30. This will be a right angle, therefore this is also the 60. Consequently, when we resolve RB, this component will be RB cos 60 and RB sin 60, and you can convince yourself of that. So that is step 1 done. Sometimes we will resolve RA and friction here, but in this example, we are not required to. So step 2 now is to resolve vertically. So when we resolve vertically, the sum of the up forces will equal to the sum of the down forces. The only up force in this question is RA, and the only down force, the down forces in this question will be the weight of the load at C, so that is 3 mg plus the weight of the ladder, mg. When we simplify, we get RA is equal to 4 mg. We can call this equation 1. When we resolve horizontally, the forces acting to the left will sum and equal to the forces acting to the right. And that is true because the ladder is in equilibrium. So the forces acting to the left will be friction, which is maximum friction, again, because we're in limiting equilibrium. And maximum friction in limiting equilibrium will be the coefficient of friction mu times the normal contact force, in this case, RE. So the forces acting to the left equal the force acting to the right, which is RB. And that will be equation 2. Of course, since RA is the same as 4mg, mu times 4mg is equal to RB. Finally, we're going to take moments about the point A. So moments about the point A, as per formula, it will be the distance from the pivot point A to C, and that will be A. So A times 3mg cos 60. Cos 60, of course, is a half, plus the distance from A to the halfway point times the perpendicular component of force acting here will be 2A times mg cos 60. And again, cos 60 is a half. So that will sum to give us the forces acting in a clockwise direction, and then the forces acting in an anti-clockwise direction will be this component. So it'll be that distance here, 4A times RB sine 60. So that will equal to 4A times RB sine 60, of course, is root 3 over 2. Simplifying, we have 3 over 2 AMG.
See you tomorrow.
Okay, all right, good.
All right.
Bye-bye.
Good evening.
All right, you too. Plus AMG. And all of that is equal to 2A root 3 RB. Now we know, so that will be equation 3. We know from equation 2, well, we can simplify here. 3 over 2 AMG plus A, that will give us 5 over 2 AMG is equal to 2A root 3. RB is the same as mu times 4mg. So we can solve for mu. We can divide mu by AMG, so that will cancel out, that will cancel out. So we have 2.5 divided by 2 root 3 times 4. And that will be equal to mu. We can type that into our calculator. So delete something here. And so we have 2.5 over 2 times root 3 and then times by 4. And then when we, because the calculation involves G, we want to round to 2 or 3 significant figures. So mu will equal to 0.18. 2 significant figures. And that completes the presentation.